for continuous distribution of charge, we shall start with if the charge is along the line. So one shall say for a linear distribution of charge. Before I go deep into this, is to just highlight how you can be able to enjoy this course. If you go in David J. Griffith's book, chapter 1 is all about vector analysis. You could have studied mathematical methods in physics, but maybe you were told how to differentiate, how to integrate, but it might have not been into the direction of physics. For example, if you look at a filter as an integrator or a differentiator or a differentiating circuit, it's different from when I say find the integral or work out the differential equation. You get what I mean? If you were to look at the capacitor, capacitor's equation or an inductor's equation, it's different from when someone just lists an equation and says differentiate or integrate. So this vector analysis chapter gives examples that are physics oriented. So it will be able to, when we talk of the car, and we are talking of the car in terms of electric field, is different from a car in vector analysis, I mean vector calculus and mathematics. So someone will say, find the curl of this expression of this region. And then you are not able to see what the curl means in terms of when you talk of an electric field. So I would implore you to read this chapter 1. The book is freely on web. It's in soft copy, so they are readable here. Also, you try to work out, and he explains very well. David explains very well. He tries to make it so natural because he was using the examples of what he was working on. So it's not like someone writing a pamphlet and then just copies and dumps things. The book flows. Electrostatics then comes in as chapter 2 onwards. Otherwise, chapter 1, he just reserved it for the purposes of your understanding. So for a distribution of charge, we shall take an element of charge, that is an element there. Just it's a matter of chopping off a little bit of this line. So it goes on and on, but we can only draw a section of it and take this element. If we can work out this element, then we shall be able to find out. So if we were to have a point somewhere, distance r, point P in space, that is x, y, z, and at a position vector, or at a position P, with position vector r, with respect to the element, then we can find we can do a little bit of things, and that means compared to when we summed from I is equal to 1 up to n of the charges that we had in order to look for the force. Remember, we summed all this, and add QI over RI squared, RI width. When it comes to the, when it now comes to a continuous distribution of charge, I already said we stretch our summation to an integral. So this will now transit to integral over the line of the charge. And then the charge now will be the same as, because this is the element, and the whole line is having charge density lambda. So if it is a line, the density will be divided, it will be the charge divided by density. So in an element of charge, I mean in this element of the line, we have a Benon charge. Okay? Implying that the charge density will be the same as the element of charge divided by, and we are interested in the charge that is contributing. You can blind yourselves from these other parts of the line and consider the L, this part here, to be the 1 point charge, and then affecting another point charge, test charge that you would have placed at this point, P. That is how I want you to look at it. Don't look at it as some line here and then some point there. This line here is going to contribute. In electricity and magnetism, you were able to see that if you had a ring, and this ring is, sprinkled with charge, okay? For example, if you got a ring and put some glue on it, and then you get sim. I normally use the example of a lumbo. Those things which they use sugar and put together, and then you chew them around. So if you were to sprinkle that kind of, or if you were to sprinkle the millet pieces all around, assuming the millet grains are charges, then you would have this whole ring being a charged body. The farther away you go was X, and this was a given point P. And you were able to extrapolate and say, as you move farther and farther away, if the ring had an area, a radius A, and this is the distance X from the center of the ring. So as X becomes larger and larger and larger than A, then you remember the whole ring was being considered as a point charge, because of how it ended up giving the E equaling to Q over 4 pi, eventually being X squared, and then if it was V being the same as Q over 4 pi, is an epsilon naught somewhere, epsilon naught X. So that's what I want you to put in your mind, that my charge, we are having a line of charge, this whole stuff, but once we take this element and it is constituting a Benon charge dq, so we are considering this Benon charge dq and a test charge that we could place around here, and these two now to be taken as two charges, and then we can apply our business of either Gauss law, which helps us also to go further to get electric field intensity. We can go further and get electric potential. So it's all about, you get the force, remember, in the classical mechanics, you move the head and got the work done. From the work done, you talked of energy. From energy, you went further and talked of potential energy. Same thing in this course. I don't know how to cover it in this one. So I will have to get my charge, Benon charge, which Benon charge now, by making it the subject, would be equal to lambda. I'll just write it in a funny way so that it looks a bit confusing, and say that this will be along the R over 4 pi epsilon naught R squared, and then lambda. just to confuse you. But the lambda dl, it's similar to having said that this would have transformed into lambda, okay, dq over 4 pi r squared, r roof, which is equal to lambda dl over 4 pi epsilon naught r squared, r roof, but I can write it as r roof 4 pi epsilon naught r squared, and then lambda. This is a scalar, so it doesn't matter whether I say delta times the scalar or scalar. If f is a scalar with my a, fa is the same as a, it doesn't matter. And that means where lambda is called the linear charge density, where lambda is the linear charge density. So we've only just managed to get the transformation, but we haven't actually gotten to the point where we stopped yesterday, where we had our EP being the same as the Q over 4 pi epsilon naught r squared r. So I now bring in the electric field intensity experienced at this point due to the field that is resulting from this elemental charge or due to this element, that when I integrate along the whole line, then I will be able to get. So it depends. If it is a straight line, you will be able to know where to integrate from to. If it is a ring, then you will be knowing that to go around a circle, I will start from 0 and I will go up to 2 pi if I'm using the angle bit. If I'm looking at the length, then I will be having 2 pi a as the circumference. So you also have to be keen and understand that we have an idea of Cartesian. So that means for Cartesian, for example, we'll be looking at the circumference. When we look at it in terms of cylindrical, then we have expressions for either the L or the S or the tau in terms of, so if we look at the L, the S, and the tau, by the way, is right in T and you rub the top. So if you have a rubber for your pen, it becomes easy. Just write the T and rub. But you can learn how to do that by rubbing before you write, so that you just put this on. So these ones can be, they have different expressions in the Cartesian. For example, in the Cartesian you have dx, or then or dy, or dz, depending on how you're along which line you are, along the x, the y, or the z, or along the z, y, x. Depends. You shouldn't be fixated with that the z is along the y. If I had a cube and I put it here, and then you already marked along the vertical z, and then the x and the y, and then I make it lie down like this, then I'm sure z will be now lying down. So here it would be the x dy, or it could be the x dz, or it could be z dy dz. That is when we are on this part. And then here we will be having the three of them. That's why we have an integral here, we have double integral here, and then here we can have the x, y, z. I don't see any other combination but can come in, and here we will be talking of the triple integral. So this would imply that our electric field intensity experienced or felt at P would be the same as we have our, this is a constant, so we can put it outside the integration command or outside the integral, and then we integrate over the line, and then we left with these other bits in here, which is R roof over R squared dl. I could put the lambda, I could leave the lambda here, or I can actually put the lambda on the outside here. But for heaven's sake, let me put the lambda there. Of course, we had not talked much about the R roof in our writing, so it's now time to define it. So R roof, where R roof is the unit direction vector point from the element of charge, dl, from the element of charge, not from element of charge. If it was element of charge, I would say the Q, but element of charge, or the element which is constituting the charge, dl, the observation point, P. So this is the other roof, is this one here. If we put an arrow there and put the roof. And the R is the distance from the element of charge, and the R is the distance from the element of charge to the observation point. I think it should be observational. This is just to set the record straight, so that we start off from the best point. So the second one, yes,
is that element of, I thought it is.
That's what I said. If it was to say element of charge, from the element of charge is not the element of charge. It's the element that has the charge. Yeah, that is the element of charge. But if I was to say element of charge, then I would say the Q, because I'm talking of the charge. But the L is the element of charge, the element that houses charge. So if it is a wire, if I slice off that small element, is the element of charge.
Next dimension, I think it is okay.
Well, the K, I think so. You are right. Since we are bringing in this business, then we should also have our 4 pi epsilon naught inside. I guess that's how it should be. Or you can put the K outside. Thanks for that. So there should be, the left hand side should be equal to the right-hand side. In the interest of conserving chalk, I will now rub off this and bring the surface, the surface charge distribution, and put my surface here, and have a small surface chopped out. The others remain the same. So this is for a surface charge, surface distribution of charge. And then the only thing that changes, or the only change we get, is about changing from this notation here to a notation now which is the S, and this is sigma. So if the charge density is sigma and the charge distribution has an element we are taking out as the S, so take the this one like a hanky, okay? If I had a hanky, the hanky is not uniform, okay? It's having values. If you would get your hand and you put it on the table, it cannot be dimensioned, its dimensions are not well defined. So if we cut out a small piece of this area here, which could be the X, the Y, depending on in which space you are dealing, then we would have this element here multiplied by the elemental charge density, then we will be able to get the elemental charge. So here, once we put everything there, we are having sigma here, we are having S here, and where sigma is the surface charge density. And I have to define this. I've defined. R still remains the same business, but this now will be, I don't see any big difference apart from here, the S, the observation point, and the rest is the same. Yes?
About that one,
Well, now it becomes a surface. So you say this is a surface. Now I can see you are getting the thing. You can use we are using the word surface, but you could have just had this to be looking like this. You can say EP is equal to 1/4 pi epsilon r integral, double integral over the surface S. That surface was, this whole surface was S, the whole of it. And then you have the other business, R root of R squared sigma ds. Or it could even be just one integral. If it is a closed surface, in the future, we shall be using this closed integral. If it is a closed surface. Just like we were talking of the work done in a closed surface. If you move from here to town and then move wherever you are moving and come back here. So we shall be using this, and normally we put an S down. And if it is a surface, we know that it is the X and Y. If it is the Cartesian, cylindrical and spherical, we shall see what the identities say. And I put a file of identities on web. It is called vector identities. This is how you transform in Cartesian coordinates. How are you able to look at a line, a surface, and a volume? When you go to cylindrical coordinates, how are you going to, how is the a line of charge or a linear charge or a line looked at the surface and the volume. And then in cylindrical coordinates, what is the expression for a line, surface, and the volume? Now, if you had, I thought of like a pumpkin or watermelon or a potato, any of those, then we can talk of a volume. So now I'm going to the third one. This was second. There should have been a 2 here for the surface. So now 3 is for a volume distribution of charge. So I will draw it a bit nicely. I could have shaded it to show that actually it is, in some books you will find it is shaded, especially like that of Rowland and Cosson. And then I take a volume, I slice a nicely put volume here and have this as our guitar. And if it is having it's a whole surface of volume tau and has volume charge density rho, it is all sprinkled with charges all over to have a density rho. These remain the same. The only thing that changes here now is rho d tau, and here this is now a volume. And this now becomes volume charge density. And then I have these as rho tau. And this is a volume. I'm conserving the chalk, but also to show you that there is nothing changing apart from looking at a different surface. So this is rho tau. You can have this now as triple integral tau. And then any other I haven't changed. This is the volume charge density. Then we have tau. Anything I haven't changed to fit within our volume distribution. So, but why are we interested in the electric field density? Why is it that we are more interested in finding? First of all, once we have electric field density, E, we can get our F, which is equal to Q. So we can derive our force from the, and in the future we shall find out in electricity and magnetism, we realize that we've got an expression which we shall get again soon as E being minus grad V. And if you have E, you can get the potential. That's the reason why we are looking at especially E rather than now looking at the force for this distribution of charges, the potential for this distribution of charges. But we shall also be able to derive them when we reach the section of electric potential. We cannot do much without considering a couple of laws, and that takes us to the Gauss's law. So we shall look at Gauss's law of electrostatics. Gauss's law of electrostatics. When you have electric charges, electric field lines, I did not repeat this business of a positive charge produces electric field lines which are outward. This is only on the condition that, this should be emanating from the center point. In electricity and magnetism, you were able to be told that positive charges are sources and negative charges are sinks. So, assuming these are not so near each other, we will be having the negative charge producing the charges outward. So, this is a sink. So, continuing with my disclaimer which I made, even in real life, even if the woman is working, she still wants to take your money. Because we take credits to be negatively charged. Not that you are negative in attitude, but in terms of the charge that you, so the guys always have to give out. There are ladies who give out their money now, and then the ladies are always, I will not use the word sing because we want to be sounding nice. Now, this is what you did in electricity and magnetism, and I doubt the positive and negative, and these charges are able now to have field lines going to them, and so that you are able to see these ones getting in and these ones getting out. And then if you have positive and positive, you are having these charges, field lines getting out, but heading each other, and building what would be the same as what we will do in magnetism as the neutral point. The same neutral point would be observed by the negative charges, neighboring negative charges, but now they will be taken in. The charges will be coming in, but still you'll be able to get a neutral point. So it's all about these field lines. Field lines properties in the electrical magnetism, we've got properties that they should not cross each other. They emanate from the positive to the negative. If you want to know the strength of their strength, you get a tangent along its curve and you'll be able to get the force. They are carrying EDC. So it's all about these field lines, and when we get a bunch of them at a given point, and they are grounded together, then we are able to talk about their intensity. And so we talk of electric field intensity. When we look at how many are moving through a given area, then we talk of flux. That's how we were able to, or how we are able to move from one point to the other. Field line, many of them at a given point, we get an intensity. If this intensity is related to a certain area, then we talk of the flux. So when we talk of Gauss's law of electrostatics, we are now interested in knowing how is now this electric field intensity related to a given area. And then we talk of the electric flux. So sometimes we call it flux theory, Gauss's flux theory. So the electric flux through a surface space is given by the integral along all that closed surface. Then we have E dot ds. The reason I was saying that the way these are related. And then depending on how much, how many charges are in this distribution, then we talk of the 1 over epsilon naught integral, not integral. If we are having dotted charges around, then we talk of the summation if we have this width. So from I is equal to 1, n, then we have our Q, I. In other words, if we were to look at this as a collection of all the charges, then we will be able to talk of it as the total charge, where summation I is equal to 1 to n Qi is the total free charge enclosed by the surface S. So if we were to put our S here, so we can now make it look a bit more beautiful as integral over the surface S E dot ds is equal to the enclosed charge, which is Q enclosed, then divided by how permittive this kind of place, region in which they are, residing is. So we divide by epsilon. So this is called the integral form of Gauss's law, or Gauss's law in integral form, because of the integration that we do. Where, of course, some of the things we have said, but I now have a new, this is enclosed, this is En for enclosed, so it's Q subscript enclosed. Where Q enclosed is the total charge, total charge enclosed within the surface S. Enclosed within the surface S. And this result, this one here, this result here is the integral form of Gauss's law. The integral form of Gauss's law. You'll find in some books they do not put the other S because of Gauss's. So you find in some textbooks, instead of Gauss's, we just put like that, and Gauss's law. I don't care. I can write as many S's as I can, so I always say Gauss's law. But you find in some literature, or in most literature, being written like that. Now, the differential form of Gauss's law is the differential form of Gauss's law from electricity and magnetism. divergence of D is equal to rho, or you will find in some textbooks whereby it is made more where D is equal to epsilon A. So you have the divergence of D equal to rho over. Well, depending on which media, in which media it is placed. If it is in free space, then it will be epsilon naught. If it is in any other media, then we can take the permittivity be epsilon. In order to apply Gauss's law, our surfaces must be symmetrical. If it is a sphere, we should look at a sphere being that nice spherical surface. It shouldn't be something round and somewhere it is missing. If it is a cylinder, it should be a nice cylinder. It should be cylindrical and spherical. So we note that symmetry is so crucial, or is vital. Symmetry is very crucial when we are applying in the application of Gauss's law. The reason we do that is because when we are trying to apply Gauss's law, we try as much as possible to create another fictitious or another virtual surface. So if, for example, we have a sphere like this, if we have a charge distribution, for example, if we had a Ntungo, I've already explained what a Ntungo is. It's some women from some place, we normally make them, so they make sim, grains to come together. I don't know how the sugar is made. It's nice to eat, but it sticks on my teeth, so sometimes I don't eat it. So if your charge distribution is that, round piece of Ntungo, in order to know how much or you can apply Gauss's law to find out, because everything is, the other one is integral EWS is equal to Q enclosed and epsilon r. So if you want the electric field density inside, then you make sure that you have your fictitious or your virtual surface inside. And this surface in electricity and magnetism, you were able to call it the Gaussian surface. So you talked of Gaussian pillbox, Gaussian blah blah, etc. If it is on the outside, if you were to put it on the outside, if you wanted the electric field density outside, then you would draw it on the outside. And this would be your Gaussian surface. That's why symmetry is very important. So we can talk of spherical symmetry, we can talk of azimuthal symmetry, whereby, for example, when you look at the cylinder and you have the charge along the axis of the cylinder, you will be having the electric field density coming out on all sides of the cylinder, but when it comes to this other side of the cylinder, some charge which is going this way will be opposing the charge which is going this way, and that one is really not going to affect anything. So if you drew a Gaussian surface around the cylinder, it wouldn't be affected by this other charge which is on the ends of cylinder, or the bottom and the top or the sides of the cylinder. I don't have a piece of paper to draw for me to mimic for your cylinder. So as a way of having something to go home with, we shall look at the case of spherical symmetry. Since we talked of symmetry being crucial, then we can start with one case of spherical. Can we have linear symmetry? How do we align? We can't really think of symmetry of a line. So basically we shall be looking at the two symmetries. One will be spherical and the other one will be cylindrical. How is the course so far? Hard. So we choose for the Gaussian surface a sphere. We choose for a Gaussian surface a sphere, concentric, they share a center. When they are wives, you say for wives, they are spheres because they share a center, you say concentric. And if they are cylinders because they share an axis, we say coaxial. That's why you talk of coaxial cable. Because they are cylinders which are sharing an axis, coaxial. They are spheres sharing a center, concentric. They are wives sharing a husband, coaxial. They are not co-husbands. It is illegal. With the charge distribution, so concentric with the spherical charge distribution. So we start by doing an example. And the example is our tomb. So I normally do not say find, but this example is to find the electric field intensity, to find the electric field intensity if you had a charge distribution which is, that is at points outside, inside, at points outside and inside a uniform spherical distribution of charge. Distribution of charge having a charge density it is a sphere. So don't confuse S for surface and S for sphere to start talking of sigma. It is a sphere, so it's a volume. So when we talk of charge density, so this charge density is rho naught and radius capital R. So I will do the outside, you will do the inside. Your 3 times. And that. So our tungo is here. I'm not good at drawing this here with free hand. and I don't have a campus. So I am having charges, this Simpson inside here. Okay? And these two more form of having radius r. My first request is to find the electric field intensity outside. This is my part. Your part will be to find the what? Inside your free time. In order to find this electric field intensity, I can apply Gauss's law. Since this is a uniform distribution of charge and is even spherical, my life becomes easy. So I will draw a virtual Gaussian surface around my charge distribution, and this I give it a radius small r, and then this one, of course, is the Gaussian surface. So I want you to understand that this surface could be just near, could be far away, it doesn't matter. I could have drawn this whole thing around here, or it could be around here. Doesn't matter, but of course it matters that you should be drawing it near where you can experience the electric field. If you were here and you draw it up in Kuruma and your charge is very tiny, you just like you guys come and hang on my office to get the wires, because that signal is the same as if you were having the electric field intensity going out. If you go far away to the fence, you don't get anything, much as you would have been comfortable. When you go to the other side of the map, you find nothing. So you should also draw it near. So then I have to apply the Gauss's law. So I say by Gauss's law, by the way, before I do this, what would be the electric field intensity from your high school? Of course, high school never used to do that. It would be the total charge, okay? And the total charge would be the same as the volume times the volume charge density. What is the volume of the sphere? 4 pi r cubed over 3. So this is rho naught. This is our Q, isn't it? This is our Q divided by 4 pi epsilon naught. And then what is the radius of your R? So if you are looking at the electric field density just at the surface of the sphere, then we would be having our capital. So this would be the same as I'm not sure whether I'm doing the right thing. So we have our R squared here. This would be R squared. Oh, it is R. I'm not sure whether you guys are.
I think instead of doing use of the scale.
Pardon?
I think instead we use of the scale of the sphere.
Not the volume.
Yes.
We are having a volume charge density. And unless if you give me unless if you give me the volume instead of, but we are looking at rho naught. Because first of all, E is equal to Q over 4 pi R squared, isn't it? So me, I'm looking at this Q. Okay? So that's, but it doesn't matter. I'm not supposed to get this. So you shouldn't worry. So I would be having this going Does it go?
Yes.
And then this goes, and this all had gone. So this would be rho naught over 3 epsilon. This is this one rho naught r. Okay? So this is what would be on the surface from your high school. If they gave you this question, you would quickly do this and you get this answer. But here is the point where we have to apply Gauss's law. So if I apply Gauss's law, it says that if I have to go along the Gaussian surface S, and then I'll be having E dash ds. Okay? So this whole thing here is for the Gaussian surface. That's the sphere that you have drawn. And this should be the same as the total charge enclosed divided by epsilon naught. That is the law. Gauss's law says this. So now I have to apply this to my tungo. Alright? So what do? I say integral over the whole of my sphere. They need me to find the electric field intensity. So I can put it outside because it is the one required. It's a dot product, so I have no problem. And for now, I may forget about the issues to do with the vector so that my life becomes easy. So let's see how it happens. So I have to integrate all over the surface, which is a sphere. And then what I'll be integrating, eventually when I integrate my ds, this would be the same as what would be the total charge enclosed by this sphere. I have a tungo, but I'm looking at, I drew another surface around it, like I put it in a cavera. How much charge would, cavera doesn't change its charge, okay? So this whole thing here doesn't change any contents of this tungo here. So the charge would be due to this one, and that charge would be the volume of this tungo, which is the capital R times the charge density. So on this other side, I'll be having 4 pi R cubed over 3 rho naught. But on this 3 epsilon naught, on this side, the area I'm considering is the area that encompasses all my everything, including so it will be so. But that area which is going to be producing where my Gaussian surface is, will be now E integral so what is the surface area of the sphere? 4 pi? This is small r because I'm looking at the whole surface. In your free time, when you are finding the one inside, it means now you are inside. And when it comes to the charge, it means you have already took out some part. Eventually, when you are looking for the one is when you draw your Gaussian surface inside, it's like you have been greedy and you have stood that part, and that means you'll be having small r and small r on both. You try it out and see how it works. So I'm integrating. So when you are integrating here, the issue is to integrate the integral. So you have gotten the whole area but you are still integrating over the surface. So that means I will be saying like this. This will be the same as 4 pi r cubed rho naught over p epsilon naught. Well, I think you can finish out that. The concept is that having our E, so this 4 Gauss, pi Gauss, so I will be having E is equal to rho naught r cubed over 3 epsilon naught r squared. Basically, we had rho naught r over 3 epsilon naught from high school, isn't it? And in high school, this E would be gotten as the electric field immense at the surface. So if we had drawn the Gaussian surface on the surface of the sphere, what would be the radius of the Gaussian surface? So if we put here capital R, we will end up with the high school stuff. Okay? So you can write it nicely like how we have started doing it at the university, as E is equal to rho naught r cubed over 3 epsilon naught r squared, and this electric field will be moving along the radius of the Gaussian surface, and this would be the same as R roof. So it's along, and this is for the case of when the Gaussian surface has a radius greater than the radius of the charge distribution or of the tomb. So you work out by tomorrow, come when you have worked out the inside, whether you have chopped off the bit and your Gaussian surface